Hello and welcome. In today's video, we're going to be just doing lots and lots of examples of computing Taylor series. Uh, so let's just get going really quick here. I'll assume you know the basics, but we'll just write down the essential facts of what we're going to do. The idea is f of x is some function that's infinitely differentiable, and we can write it as, we can express this function as the sum from n going to infinity, or n going from 0 to infinity, of the derivative of the nth derivative of f evaluated at a all over n factorial of x minus a to the n power. So this is a Taylor series of f of x, which is a function that's infinitely differentiable at x is equal to a. So that's where it's expanded about. So of course you're going to get a different Taylor series for a given function by expanding about different points a. So we always have to specify where we're starting from, essentially. Okay, so I'm going to do just a ton of examples of this. And we're going to actually start with some of the simplest examples first, and then move to things that are a bit more complex. Okay, so let's start with maybe the most basic example of e to the x is equal to f of x. All right, so this is, call this example 1 that we're going to do. All right, so, and the procedure to find a series, of course, is we really have to just find f of n. Oh, back up here for a second. I always have to indicate from which point we're expanding. So in this case, I'm going to do, again, the most basic, x is equal to a is equal to 0. All right, so this is the most simple one to do ever. So let's just do it quick. First off, we really, the goal with all of these is to find f, the nth derivative of f, evaluated at a. In this case, a is 0. So that's what we have to find. And to do that, we really have to pick up on some patterns here. So we have to do that for all n, starting at 0, 1, 2, and going up forever. All right, so really it's about finding a pattern. So let's do it. Okay, so x at e to the 0, of course, this is for n is equal to 0. E to the 0 is, of course, equal to 1. N is equal to 1. Well, we can do this one as well. We know that the derivative of e to the x is e to the x, and we're going to evaluate it at a equals 0, which is going to be e to the 0, which is equal to 1. Then n is equal to 2. Well, the derivative of e to the x is e to the x, and the second derivative of e to the x is e to the x again. Evaluate at 0, we get 1. So actually we find out the simplest possible derivative ever, which is going to be f to the nth derivative, evaluate at 0, for e to the x is actually just equal to 1 for all n. Okay, and this, of course, is probably the simplest derivative expression ever. So anyway, we have it now. So f of x, which is equal to, in this case, to e to the x, has the series, the sum, starting at 0 and going up forever, of 1 all over n factorial times x to the n. All right. So many of you who are a student of Taylor series probably already knew this one. You may even have it committed to memory. And if you don't have it committed to memory, consider this is probably one of those series that you really ought to have committed to memory because it's very, very useful. It's very common, and having it at the ready is good for solving many problems. Now let's go on to another one. Well, we did e to the x, so why don't we try natural log of x? But this time we're going to do a little twist here. Let's do expanded about a is equal to 1 instead of, we can't expand, of course, natural log at a equals 0 because natural log is not defined there. All right, so let's do it. Of course, we have to now go, let's do n equals 0. We have natural log of 1, which is equal, this of course is f at the 0th derivative. We're evaluating at 1, and this, of course, is 0 in this particular case. Now we have to do n is equal to 1. So we know that the derivative of natural log of x prime, of course, is 1 over x. And now we're going to take this whole thing, and we're going to evaluate it at 1. And we get 1. All right, now we have to do n is equal to 2. And we're going to take the derivative of 1 over x now. Take the derivative of that, and we get negative 1 over x squared. And then we, of course, take that whole thing and evaluate it at x equals 1, and we get negative 1. All right, so we're on to a good start. I think we have here, we've figured out it's 0, 1, negative 1. I don't know if we quite have the pattern yet, though. So let's try n is equal to 3. And of course, what we do is we take negative 1 over x squared. We take the derivative of it. We're essentially taking the work from the previous one and then taking the derivative of it and going from there. Right, so now, of course, we have to, what we have is now 2 all over x to the third power, and it's a positive 2 because of the chain rule, or sorry, the power rule. And now we have to evaluate at 1, and we get positive 2. I'm going to go one more, do n is equal to 3, or sorry, n is equal to 4 here. And we're going to take, what we have here is 2 times x to the negative 3 power. Sorry, we're going to take the derivative of this. And of course, we're going to get 2 times negative 3 x to the negative 4. And we're going to evaluate that, this whole expression, at 1. And we're going to get, of course, negative 2 times 3. And of course, we're starting to see a pattern now where this is going to be a negative 3 factorial. Okay, we can see this, of course, as positive 2 factorial down at the n equals 3 case. All right. Okay, I think we're starting to see a pattern emerging here. Okay. I can guess now what n is equal to 5 will be. We see that there's an alternating sign, so I'm going to ask a question. Without actually computing it, I see that there's an alternating sign. And there's also a factorial. And what it really looks like is that there's actually an n minus 1 factorial is the real key here. All right, so what I'm going to guess now is that f, the fifth derivative here of x, well, it's going to, evaluated at 1. I think we have it here, and this is going to have to be, if n equals 4 was negative 3 factorial, I bet it's going to be positive 4 factorial. Okay, and of course, f to the n, evaluated at 1, is going to be, we have to put a negative 1. That gives us our alternating sign. We have to figure out where are we going to start, where is our sign going to start. And I see if I have an n plus 1, that should do it. That should give me what I need, because what I want odd powers to be positive and even powers to be negative. And now I have to write here, and then I have to have an n minus 1 factorial, and then that gives us that delivers us our pattern. And of course, there's no way to figure this out a priori. You really have to just compute many examples till you see the pattern emerge. Okay, so now what I'm going to do is I'm going to write down the natural log of x can be expressed as a Taylor series now, and starts at 1 and then goes up to forever. And the reason I'm starting at 1 is notice that n equals 0 has a 0 derivative anyway. Therefore, I really don't need to the n equals 0 case has a 0 value. So I don't need to add that first term in there. So I can start at n equals 1 instead of 0. Okay, what I have here then is I have that alternating sign. Then I have n minus 1 factorial. And of course, we're going to divide the whole thing based on the formula for Taylor series by n factorial. And then I'm going to take x minus 1, because that's where we're expanding about, to the n power. One thing to note is that if I take an n minus 1 factorial and divide by an n factorial, that's the same thing as n minus 1, n minus 2, all the way to 1. And this whole thing is going to be n times n minus 1 times n minus 2, all the way to 1. And we can see that all of these are going to cancel right there. And that's going to yield, of course, a 1 over n. So I can write my final answer here a bit more simplified as negative 1 to the n plus 1 all over just n x minus 1 to the n power. And that then is my solution. I can box that up there as my answer, particularly right here. That's really the answer I'm looking for. Okay, all right, so I think we've knocked out 2 simple examples. We've built on them progressively. All right, so now I'm going to do another example that's a little bit more complicated, not much more complicated. So now let's do my third problem, which is going to be f of x equals 1 over x. But we're going to expand now at 2. Okay, so let's do this one. So f, the 0th derivative, which is just, and we're going to evaluate it at 2, that's just going to be 1/2. So that, of course, is n equals 0. Now we're going to do n equals 1. We'll have to take the derivative of 1 over x. Of course, that's going to be a negative 1 over x squared. I'll just compute some of the derivatives here. And that's going to be, again, we can take the derivative of the previous problem there, and we're going to get a positive 2 times x to the negative 3. And then n is equal to 3. We're going to see here we have a 2 times x to the negative 3. We just take the previous result from the above line. We take the derivative of it, and we get a 2 times 3, and we make it negative now, times x to the negative 4. All right, now for all of these, then, what I can do is then go the f prime of 2 is going to be equal to negative 1/4 here. Or I think it's better to write this actually, is to not simplify it so much, but actually write it as negative 1 over 2 squared. Okay? And now for the n equals 2 line, what I'm going to do is I'm going to write, this is actually 2 over 2 to the third power. That's equal to f second derivative evaluated at 2. And then finally, f the third derivative evaluated at 2 can be written as negative 2 times 3 all over 2 to the fourth power. Okay, so I think I'm actually, I think I see the pattern emerging. First off, let's make a few comments here. This is clearly looking like an n factorial up there, right? And this down there looks like a 2 to the n plus 1, right? Because n is equal to 3, and we see a 4 there. All right, so I think I have the pattern written down. I can write down the pattern. Now f to the n then, evaluated at 2, is equal to n factorial, divided by 2 to the n plus 1. Now the only thing to do now is note also, maybe I should have written that in red, is look at that and see that that's actually a negative 1 to the n power. All right, because odd powers are negative and even n values are going to be positive. So I need to put in, a negative 1 to the n there. So I think I've got it now. I have my Taylor coefficient derivative value sitting right there. So finally what I do is I write down f of x is equal to 1 over x, which has the Taylor series about 2, and this is going to be n equals 0, all the way to infinity. We're going to sum this up, and this is going to equal negative 1 to the n power times n factorial all over 2 to the n plus 1, right? But then we have to, of course, divide by n factorial. Of course, these will cancel. I'll do that on the next line. We're going to go x minus 2 to the n. So now I'm going to simplify up my work here a little bit now that I've canceled my n factorials, and just write it as negative 1 to the n all over 2 to the n plus 1 of x minus 2 to the n power. All right, so that right there is my final answer for this problem. Okay, all right, I'm going to do yet one more final example. And this example is actually, we're going to go a little simpler now here with this one. We're going to do something maybe a little non-intuitive. Now so this is my final example, and we're going to actually do it for a is equal to 0 and a is equal to 1. So we're going to do two expansion values. Now we're going to do it for a function which I'm going to write in two different ways. I'm going to write it as x minus 1 quantity squared, which of course when I FOIL it out gets me an x squared minus 2x plus 1. I think anyone can agree that this is a simple polynomial. And recall, of course, that Taylor series, the whole objective here of Taylor series is to represent any function, that's what I call C infinity, has infinite derivatives, as a polynomial. So the question then I think we're posing here is what happens when your Taylor series, which is supposed to represent it's supposed to represent any function as a polynomial. What if the function you want to represent is already a simple polynomial? We would hope that the Taylor series would somehow agree that it would be this, that we're talking about the same object here, whether it's you think of it as a Taylor series or just a simple polynomial. They should be the same thing. So let's actually just go through the process of finding out what the Taylor series is to this simple polynomial. One would expect that we should be, in a sense, running around in circles and not getting very far, that the Taylor series shouldn't tell us anything we don't already know. So let's try it. Okay, so now let's try the a is equal to 0 case. Okay, we're going to expand about a equals 0. Well, f at 0, of course, if I write it down, it's going to be 0 squared minus 2 times 0 plus 1, which is equal to 1. Now, of course, f prime of x is going to equal 2x minus 2, and then we're going to evaluate that whole thing at 0, and we're going to get minus 2. Okay, and then finally, f double prime of x is going to equal 2. We're going to evaluate that at 0, and we're going to get 2. And now, of course, if I go to f triple prime of x, it's 0. And in fact, f, any derivative above that, will also be 0 for n greater than or equal to 3. Okay, so I have my coefficients right here. Here are the 3 coefficients. Everything else, of course, is 0. So, what is the Taylor series? Well, I'll write it up here. F of x is equal to 1 minus 2 times x minus 0 to the first power plus plus 2 times x squared all over 2 factorial, which is just 2. Of course, those cancel those right there. And what we end up with is, of course, 1 minus 2x plus x squared. Note that the Taylor series calculation, all of the work we just did, proved exactly what we already knew. The idea here is that basically the Taylor series procedure gave us what we already knew. Okay, so I'll just put that in a few exclamation points there that it gave us exactly what we already knew. But I want to do another example now. Put a line right here. And now let's expand about x equals 1. Right, so what I'm really thinking about here is what's going to happen when x is equal to, or when our expansion point changes now. All right, so of course we know that f of 1 is going to be equal to 0 if you just evaluate it. So if I actually write it as x 0 minus 1 quantity squared, of course it's just going to be, oops, my bad. I'm going to back up here. I'm getting a little confused here. We're evaluating 1 minus 1 quantity squared, and then of course that's going to give us 0. Okay, now of course f prime of x, that's going to be 2x minus 2. We're now going to evaluate at 1, and of course we're going to end up with 0. All right, now we're going to go f double prime of x, and that's going to be equal to, I evaluate at 1, and we get 2. Now I go f triple prime of x. We get 0. And of course any nth derivative is going to be 0 for this thing for n greater than or equal to 3. We already established all of that. All right, so now here, I'm going to look again here. We see that our coefficients have actually changed. If I look at these coefficients here, they've changed a little bit. So depending on your expansion point, the Taylor series coefficients will change. But in fact, they've actually gotten even more simple. So now my Taylor series, I can write it as 0 plus 0 times x minus 1 to the first power plus 2 times x minus 1 to the second power all over 2 factorial plus 0 times x minus 1 to the third power all over 3 factorial. And of course, everything after that is also 0. So what we have here is that the conclusion we make from all of that is that f of x, after we look at all of the fact that essentially that's 0, this is 0, this is the only thing that's not 0 right here, and that's 0, and everything else is 0. There's only one term that's non-zero, and it's equal to x minus 1 quantity squared. Note, and I'll put it in green here, that that's precisely what we already knew. So the Taylor series calculation, expanding about x is equal to 1, delivered us exactly the same function as we had before. And what we have here, the main conclusion I want to make now, and I'll put this as an asterisk, is that the Taylor series, or maybe I should say it this way, polynomials are their own Taylor series. So Taylor series, it doesn't give you anything other than what you already have when it comes to polynomials. Okay, so I think that's an interesting coda to our exercise of doing doing Taylor series, to show that the examples of simple functions give you exactly what you expect. All right, I hope that these examples help figure out, gave you many ways to figure out Taylor series, and thank you very much.